Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in Applied Electronics. We are going through some of the sections on physics of materials meant for the 3rd semester students. Is a paper 3 which deals on the subject physics of materials. Now, in this paper we have got a chapter on bonding in solids, and in the chapter on bondings in solids we saw in the previous lecture the ionic bonding, we saw the primary bondings, and especially we dealt with ionic bonding. In today's lecture we will go through the lecture 3, the covalent bonding, right. What I would like to tell you at this point of time, covalent bonding is of maximum significance for the students of electronics and also electrical engineering and computer science students, because most of the devices are containing semiconducting materials which are bonded together by covalent bonding. So, let me go through the contents of today's lecture. Importance of covalent bonding, semiconducting materials, what are the materials which are used for semiconductors, and their applications, and the hydrogen molecule. That is the simplest example that one can think of for covalent bonding. Now, some of the basic ideas are, as I told you, it is the most important bond to be learnt by the students of electronics. Not only electronic students, all the people who are dealing with them nowadays, CD-ROM and cell phones and all these things, they are again the laptop and the computers and all these things are made up of semiconducting materials, the significance of which all of you know by now. You would have come across transistors and so on. So, all these materials are made up of semiconductors. Now, therefore, all semiconducting elements and compounds are mostly covalently bonded. I would like to underline the word mostly covalently bonded. What I mean by mostly covalently bonded, I will come to it at a later stage. And the most important materials which are used for semiconductor devices, the basic materials are silicon, germanium and gallium arsenide. Of course, you have got very many other systems also. So, you got silicon, germanium and gallium arsenide, that binary system like gallium arsenide, indium phosphide and so on. These materials are used for very many semiconducting devices. Now, let us spend some time on semiconductor devices. Now, what are the devices which you come across? So, semiconductor devices are electronic components that exploit the electronic properties of semiconductor materials. Exploiting what property? That the current, right. The current, as I will be telling you later, the current can be controlled in the case of semiconductors by some method, right. I will come to that later. Then, so you got the basic materials, as I told you, silicon, germanium, gallium arsenide, as well as organic semiconductors. Semiconductor devices have replaced, as all of you know, the thermionic valves. Maybe some 40-50 years back, we had computers of very big size, right. The computers were not like a laptop or pop top we are talking about, but they are huge size, something like Almira, which will be containing a few thousand vacuum tubes. So, it will be kept, it has to be kept only in a air conditioned room, and the connections are very important, that if there if the connection goes wrong, the system will not work, the computer will not work. Now, we had maybe here in IBM 1620, you have to put the chord input, chord output, and anyway the thing is you had vacuum tubes, the size will be enormous, the power input should be large, you have to have 220 volts, right, unlike your laptop. So, the power input is large, heat generated will be large, and so you have to have everything in air conditioned room, size will be large, and because of the fact that they contained vacuum tubes. Now, the vacuum tubes have been replaced by the transistors. What are transistors? You have a p-n junction, right, it is a diode, they are transistors. Now, they are all semiconducting materials, right, doped semiconductors, P, and then are some other dope, you make use of silicon or germanium, then you do doping. I think you know by now what are doping and all, but anyway we are more concerned about bonding. The semiconductor devices are manufactured both as single discrete devices as well as integrated circuits, which consist of number from a few to as low as 2 to billions of devices manufactured and interconnected on a single semiconductor substrate or wafer, right. As you see here, now you will be having a semiconductor integrated circuits, right. I told you about integrated circuits. You see the integrated circuits, right, you have got very many components, they are made up of semiconducting materials, right. You got a chip here, right, semiconductor chip, and therefore, the flow of current in semiconductors can be controlled, that is the important thing, by doping, by putting some impurities. What is doping? You are putting some impurities, and you can increase the number of electrons or the number of holes. You will be talking about, you would have studied about electrons and holes. You know, in the case of metals, the current is due to the flow of electrons. What is current? Current is nothing but flow of electrons. Now, in the case of semiconductors, you will come across both electrons and holes, which are responsible for the current. The total current will be the sum of the two components, right, the current due to electrons and the current due to the holes. Now, the current, the number of electrons and number of holes can be controlled in the case of semiconductors. The beauty is the current can be controlled by the number of dopant atoms that you add to the basic material. The basic material principally will be silicon or germanium or gallium arsenide or aluminum phosphide and so on, but the number of atoms that you replace in silicon, the silicon atoms can be replaced. These impurities are substitutional impurities. You should remember the difference between substitutional and interstitial impurities, and they are all substitutional impurities. One silicon will be replaced by some aluminum or some phosphorus. Aluminum is trivalent, whereas phosphorus will be a pentavalent. What is the atomic number of silicon? It is 14, 13 you have in a periodic table on the left side, 15 on the right side. 13 means aluminum, 15 means phosphorus. So, you can add a phosphorus. So, by adding phosphorus you are injecting one extra electron, right. By adding a trivalent impurity like aluminum, you are adding one extra hole, and so the number of electrons and holes can be controlled, and hence the current flow can be easily manipulated in the case of semiconductors by changing the number of free electrons and holes by doping either, as I told you, with aluminum or phosphorus, or similarly you can have boron, right. You got a boron, right, and again phosphorus, right. You can have 3,5 compounds, right. Some of the elements in the third column of the periodic table on the right side or the fifth, right, that they can be substituted in the place of silicon, right. Now, if you have a system in which you have got you are replacing silicon by a trivalent system like aluminum, silicon is having 4 electrons. Now, you are removing one silicon atom and you are putting a 3-valent system like aluminum. So, that means the number of electrons that you are introducing is lesser, or you are introducing a hole. A hole means a positively charged thing, right. It is not a positively charged particle, but in principle it is a positively charged thing. And on the other hand, if you are adding arsenic, right, it is a pentavalent impurity atom. Instead of a 4-valent system, it has got 5 valence electrons, but therefore, it has got one excess electron. So, for the system as a whole, for every pentavalent impurity atom that is being added, there will be one excess electron which will become a free electron. Now, therefore, by putting more number of pentavalent impurity atoms, you are introducing more number of electrons. Electrons become the majority carriers, they are called n type. N means negative. Why it is negative means because you are adding more number of electrons which are negatively charged. Okay. So, by either adding a trivalent impurity or by pentavalent impurity, you can get respectively a p type semiconductor or a n type semiconductor, and now you combine p and n, right. You have got a p type semiconductor here and you have got a n type semiconductor. You fuse these two, combine these two, that will give rise to what is called a p n junction, right. They are known as the p n junctions. They are the transistors. What is a transistor? It is a p n junction, right. You combine a p type material with a n type material. What is a p type material? It may be silicon or germanium and doped with a trivalent impurity atom, whereas n type is one in which you replace silicon by a pentavalent impurity atom, which gives rise to an n type semiconductor, right. Now, when you combine p and n, you get a p n junction. It is a diode. P n junction is a diode, that is a transistor, right. Now, you see you can have p n p, that is a 3 terminal device, right. It is a p n p or n p n, you can have different configurations. Now, these are some of the transistors, right. You see some of the transistor configurations, right. Now, the transistor era has revolutionized the mankind, right. We had vacuum tubes for a number of years. The discovery of semiconductors by Bonding, Brattain and Shockley, the discovery of transistors, it has really revolutionized the life of all, in the sense because the energy and so many other things, compactness and all these things all of by now. So, miniaturization is the most important thing, the energy requirement becomes smaller. Now, let us go through the materials which are used for devices. We are going to talk about the very many semiconductor devices. Now, the point is, in all the semiconductor devices, the bonding is mostly covalent, right. You can say covalently bonded systems, right. Now, what are the materials we are used for devices? What are the applications these devices have? Silicon is the most widely used material in semiconductor devices. Its combination of low raw material cost relatively simple processing and a useful temperature range makes it currently the best compromise among the various competing materials. So, we have got different materials, as I told you that we have got silicon, germanium, gallium arsenide. Of all the materials, silicon based systems are more important, right. They are most widely used. Let us have a break at this point and we will resume later. Welcome back after the break. I was telling you about some of the materials which are commonly used for semiconductor applications. They are mostly silicon based materials, right, and apart from silicon you can have gallium arsenide. It is a very important system. It is called a 3,5 compound. Why it is called 3,5 compound? You find gallium in the third column, right. You got a 3 valence system. As I told you, arsenic is a 5 valence system. So, a combination of gallium and arsenic, right, a 3,5 compound, or you can have indium telluride, it is a 2,6 compound, right, indium phosphide and so on. Now, therefore, anyway, you can have you got a 3,5 system which is widely used in high speed devices, but so far it has been difficult to form large diameter bowls of this material, limiting the wafer diameter to sizes significantly smaller than silicon wafers, thus making mass production of gallium arsenide devices significantly more expensive than silicon. And again you can have silicon carbide, that is again a material used for devices, right. Silicon carbide has found some application as the raw material for blue light emitting diodes. Light emitting diodes are called LEDs, as all of you know, and is being investigated for use in semiconductor devices that could withstand very high operating temperatures and environments with the presence of significant levels of ionizing radiation. This is very important, right. When you go in the upper atmosphere, the ionizing radiation level will be high. So, silicon carbide could be the material which can be used. The impact diodes have also been fabricated using silicon carbide. So, from what I have told you so far, you have silicon based materials, gallium arsenide for optoelectronic applications, and then you got the silicon carbide. Now, these are some of the examples, and you have got a variety of systems, either 3,5 compounds or 2,6 systems, or you can have, instead of binary you can think of even ternary systems like ternary pnictides and ternary chalcopyrides. The ternary chalcopyrides like AgGas2 or Se2Te2, the third system in the binary, and so the ternary chalcogenides and ternary pnictides, they are used for solar cell applications, right. So, the materials used are the indium arsenide, other systems are indium compounds, right, indium arsenide, indium antimonide and indium phosphide, and also selenium sulphide. Now, the earlier things are used for LEDs, whereas selenium sulphide is being used for manufacture of photovoltaic solar cells. Not only selenium sulphide, as I told you, AgGas2, the ternary chalcopyrite, S2 or Se2Te2, they are the chalcogen atoms. You know, sulfur, selenium, tellurium or chalcogen systems. Also, ternary chalcogenized or ternary pnictides are also been tried, so that the solar cell efficiency can be enhanced. The most common use for organic semiconductors is organic light emitting diodes. Now, let us go through the list of common semiconductor devices. As students of electronics, you will be aware of what are all the devices which are used, and especially they are made up of semiconductors, and again covalent bonding is the dominant bonding. It is a bonding which is responsible for the stability of semiconductors. Now, one should know the list of the devices, a diode, as I told you, the p-n junction, right, a diode which can be used as a half wave rectifier, as all of you know. Then you have the gun diode, laser diode, light emitting diode, LED, right. Then photo cells, the pin diode, the Schottky diode, solar cell, tunnel diode, Zener diode. These are the various devices, right. Now, of immense applications, right, in the medical field, in the communication, and so many other things, right, solar energy conversion, and very many applications are there for these devices. Let us see some of the devices which are being used now. Laser pointer. In every lecture, people are using laser pointer. So, you can have in different colors. You can have either green color, depending upon the energy levels, what the gas that you are using, and depending upon the energy levels with which you are dealing with, because the electron will be jumping from one level to another level, giving rise to a green line or a blue line. And so, you can have a blue laser or a green laser, you can have a pointer, right, a laser pointer. And the next comes a solar powered cars. Now, with the energy being in greater demand, right, because you are running out of oil and coal, and the best option will be the solar energy, right. It is the most one of the safest ways of getting energy, because as long as sun is there, you will be getting the solar energy. So, that is the best, in the sense that it will be cheap, right, provide the material that you are able to get, and the efficiency is improved, it will be the best thing, right. And again, there is no contamination or some kind of, I mean, if you go for nuclear power, you have problems, right, you may have problems, and during earthquake and so on, and that is our past experience. Now, we are trying to use solar powered cars, not only cars, the hospitals in very many cities, and the electrification is by solar energy being converted into photons, right. The photons are able to generate, that is photoelectric current, right, that is the photons are being used to generate current. The solar energy, right, solar energy is the best energy, the best form of energy you can have. And solar panels, right, I am showing you solar panels, and the tunnel diodes, all of you know, they are used for high frequency oscillators. Who found tunnel diode? What is a tunnel diode? Now, tunneling is a quantum mechanical phenomenon, right. You should be aware of the fact that when you want to explain bonding, not only bonding, the word tunnel diode means your something is going from this room to next room, right, tunneling through the wall, tunneling through the barrier. So, that could not happen for a classical particle, right. For electron, because of the de Broglie wave, the dual nature and other things, you can the electron can tunnel, right. Anyway, the point is what I want to emphasize is quantum mechanics will play a very important role in explaining the bondings, all bondings, right. All bondings can be explained only using, you have to have quantum mechanics, right, because of the fact that you are dealing with electrons. Electrons are not classical objects. So, you have electron or hole, they are not classical objects. So, classical mechanics cannot be used to describe bonding. You need necessarily the use of quantum mechanical ideas, that is what I am going to do in the lectures to come. And apart from that, now the word tunnel diode means tunneling. Tunneling is a quantum mechanical phenomenon, that should be remembered. And who found the tunnel diode? It is Esaki, Leo Esaki from Japan. It is called a Esaki diode or a tunnel diode, right. You see them tunnel diodes which are used for high frequency oscillators, and the list of common semiconductor devices, other devices apart from what I told you earlier, the bipolar transistor, the field effect transistor, including MOSFET, the significance of which the electronic students will be knowing to a large extent by now, silicon controlled rectifier, thyristor, Hall effect sensor, integrated circuits, charge coupled devices, microprocessor, random access memory, RAM, read only memory, ROM, and all these things, you know, right, electronic devices, you have the CD player and many other things. So, you have the computer, your disk and so on, read and write, memory disks, all these things are made up of semiconducting materials. Now, this shows that this gives the importance of the semiconducting materials, right. The covalent bonding, because the bonding in all the semiconductors is covalent bonding, right. So, the covalent bonding, the simplest system is the hydrogen molecule. The important point is, I am emphasizing once again, in order to understand covalent bonding, let us take a simple system, the simplest being hydrogen molecule. You look at the hydrogen molecule. What is hydrogen molecule? You take two hydrogen atoms, you combine, right. How does the bonding occur? You remember, each hydrogen atom is neutral. It has got a proton and electron. This hydrogen atom is having again a proton and electron. The two systems, two atoms that you have got here, they are definitely neutral, right. The important point is they are neutral, but you see here the atom here, right, the hydrogen atom, you have got proton and electron, then you have got a proton and electron, you have got the two electrons here, right. Now, how does attraction occur, right. The important point is that they are particles of the same charge, right. Both are electrons, both are negative charge, however, the bonding is there, right. So, the bonding cannot be explained on the basis of Coulomb's law. Coulomb's law simply states like charges or will be repelling each other, only unlike charges will attract. So, now you have got like charges, right, the electron and the electron, the two electrons. How can you explain the bonding between the two hydrogen atoms? So, that is the reason why I told you that considerable amount of quantum mechanics will play a role in explaining covalent bonding, which we will see in a greater detail in the next lecture. And the covalent bonding, you have got a electron cloud. So, as I told you, we have to make use of quantum mechanics. So, describing electron as a particle is no longer true, right. You should remember, as students of electronics, you should not be considering electron as a particle. The equivalent charge density is shown here, right. You have got the proton here, and the electron is considered the electronic charge cloud, it is not a particle, right. So, the charge cloud of the electron here, the bonding occurs here, right. Now, the bonding should be understood in terms of quantum mechanics, and so you have the H2 molecule. Now, here you can see that you have the two hydrogen atoms, right, which are coming closer to each other, right. You see an electron revolving around this one hydrogen atom, you see another hydrogen atom, but when they come closer to each other, the bonding occurs, right. The point I want to stress is these two electrons belong to the two atoms. So, the two electrons are equally shared by the two hydrogen atoms. The point is the two electrons, one electron of this atom, the other electron of the atom, you have got two electrons. These two electrons belong to these two hydrogen atoms. The electrons are equally shared, or simply I will say in the Lewis notation, the electrons are being shared by the two atoms. Let me now show another thing. This can be seen like this, right. You have got hydrogen molecule, wherein you find ultimately, see the two protons, right. The 2 points are two protons, right. The one proton here and another proton here. The two electrons belong to the system, right. You have got two protons, the two electrons are revolving, right. So, this is a hydrogen molecule, right. Now, what I have shown now is that you see from the figure, the animation, that the two electrons are revolving around the two protons, right. Now, we will pass on to this animation, wherein you find that two hydrogen atoms are coming closer to each other, right. You see the two hydrogen atoms coming, right, and now the orbital picture for the electron is removed, and you have got a charge density cloud that you are able to see, right. That the two charge density clouds are coming, right. This is one hydrogen atom and another hydrogen atom here. these two come together to form the hydrogen molecule. This is clearly a quantum mechanical approach. You do not treat the electron as a particle. On the other hand, you have to necessarily treat the electron as a charge cloud. That is what I am trying to show, because in the next lecture I will be dealing with the theory of covalent bonding in a greater detail. So, that is the reason why I am showing this picture, and also I want to emphasize the quantum mechanical approach that should be used not only for covalent bonding and to explain all the bondings in solids, right, in all systems, in living systems or non-living systems, in semiconductor, whatever be the material, metallic bonding, covalent bonding, ionic bonding, in all the bondings quantum mechanics plays a very important role. So, let me now summarize what I have told so far. Covalent bonding is of great importance for all, in the sense that all people who are using cell phone, computers, many other devices as of now, or medical or military applications, or laser for surgery, or laser for communication, optoelectronics, and then every field we have got we are using semiconducting materials, and in all. So, the people who are dealing with the people who make the materials and go for applications, the electrical engineers, electronic engineers, the computer people, information technology, all people, all the engineers and the scientists, they have to know about covalent bonding. Covalent bonding is a very important bonding, because all semiconducting devices, in all the devices, the bonding is covalent bonding. So, the nature of the bonding should be known. The nature of the bonding is mostly covalent in our semiconductors, as I told you. Hydrogen molecule I have taken as the example, because it is the simplest system that one can think of in which you have got covalent bonding. It is the simplest system. Then we can go to methane, water molecule, and so on, right. So, let us now pass on to the question session, right. You have the questions. Why covalent bonding is important for the students of electronics, right. The electronic students, I am giving a lecture for them, mostly meant for the electronic students, right, for applied electronics. Now, therefore, now you should know why you should study bonding, and again especially why you should study covalent bonding. Now, every electronic student should be having a very good knowledge about covalent bonding. Which are the semiconducting materials which are used for devices, right. Name some of the semiconducting devices and their applications. Which is the simplest system in which you find covalent bonding. Now, with this we come to the end of this lecture. In the lectures to come, again I will go through the covalent bonding in a greater detail, especially I will start in the next lecture the theory of covalent bonding. What makes two hydrogen atoms to come closer to each other to form the hydrogen molecule. So, with this we come to the end of the lecture. Thank you. We will see the rest in the lectures to come.